Hello and welcome everyone. This video is about Doolittle's LU decomposition, which puts constraint on the lower triangular matrix that all elements on its main diagonal should be equal to 1. The product of the lower and upper triangular matrix is the matrix on the right. We can compute the elements of the lower and upper triangular matrix by equating the corresponding elements of this right side matrix with the coefficient matrix A. Let's solve these equations when I is equal to 3 and j is equal to 2. In this case, I is greater than j, so we'll be getting an element of the lower triangular matrix, which is L32. The summation index P will only contain one value, which is 1, since j minus 1 is equal to 1, and summation from 1 to 1 will contain only one value, which is P is equal to 1. Once we plug these indices, we get this equation, which can be rearranged to get the same elements in index 3, 2 in matrix A and the right side product matrix. Similarly, we can also check the calculation for I is equal to 2 and j is equal to 3. Now I is less than j, so we will compute an element of the upper triangular matrix. The summation will again contain one index of P, which is 1. The resulting equation looks like this, which can be rearranged to show that it's equating the elements from A and the product matrix at index 2, 3. As said in the previous video, which was on LU decomposition, the next steps to find a solution include forward and backward substitution steps. It's a common practice to store the elements of a lower and upper triangular matrices in a mixture matrix. The forward substitution can then be calculated using this formula. Let's now see how we implement this decomposition in a Python code. For that, we write a function, Doolittle Decomposition, which takes the coefficient matrix A and the output vector B as inputs. Then the first row of A is the same as the first row of U matrix, so we start from the second row. Then we loop over the columns, and if the row index is greater than the column index, we update the lower triangular element, otherwise we update the upper triangular element. After that, we run the forward substitution followed by the backward substitution. This is the code for forward and backward substitutions. Let's see how we can solve this curve fitting problem using the Doolittle's decomposition method. Like before, we only need to make two changes in the curve fitting code. We import Doolittle decomposition function from utils and use it on line 24. Rest of the code remains the same. The solution is again the same, that is a quadratic equation with a equal to 3, b equal to minus 2 and c equal to 4. This is all about Doolittle's decomposition. I hope you liked this video. Thanks for watching. Please subscribe and see you in the next video, in which we will talk about Kraut's LU decomposition method.